Welcome back. So in the previous lecture, we came up with this model, the simulink model, using the simscape electrical library. And I've made a couple of changes, nothing too significant. I forgot to add the ground reference next to the PWM generator over here. That's one thing that I've added. And I've also added a solver configuration over here. Basically, these blue components that you see require this block to be attached to them in order for MATLAB to be able to solve them. And one other thing that I believe requires a bit of an explanation is this little block over here. There's two arrows. This is a simulink to physical converter. What does it do? It allows this black block to communicate with this blue block. These black blocks are naturally simulink blocks, and these blue blocks are physical components, in quotation marks, in the simscape library. So in order for these libraries to be able to communicate, you need to use this little block over here. This is just the opposite of this. This is a physical to simulink converter, right? And one other thing that I've added is this two workspace block. I did away with the scope because it does limit functionality to a certain extent. And this gives you a lot more flexibility in the sense that you can plot the results on your workspace. You can do all sorts of crazy things you want to do with them. Right. Other than that, everything else is the same. So here's our MATLAB script. Let me just add the script over here to the path so that we can run it. From the command window, I'm just going to press run instead of typing the entire name here, and we'll wait for that to run. So basically, as we went through the previous lecture, what this script does is it works out the required values for L, C, and any other value that we needed to calculate. And we're designing right now for R equals 2.5 ohms. So once this runs, got a couple of windows open, so it is going to take quite a while. Once this finishes executing, I am going to actually run the circuit, run the simulation, then I'll present the results. So for now, I'm going to pause the recording and I'm gonna holler at y'all later. All right, so we've run the simulation. One other thing that I neglected to mention is that this workspace block should save data as a time series, as you can see here. And you can name the variable whatever you want. I've named the current and voltage, right? So now we're going to call the data from that workspace over here. And let's refer to the current as I1. And let's call current. And let's refer to the voltage as V1. And let's call voltage. Right, so I'm just gonna save this on I1 and V1. Then the other thing I wanna do is that I want to change the load resistor from 2.5 ohms to say 20 ohms. And there's reason to my madness, not 0, 20, there we go. And let me just make sure there's no clear all script over here. Yeah, there's nothing. So I'm gonna rerun this, then rerun the simulation, and we'll see what the difference between the 2.5 ohm and the 20 ohm load is. So right now I'm gonna pause the recording and I'll resume it as soon as I've run the second simulation. So we did the second run, and as with the first run, I'm going to store the results in separate variables. So I'm storing the current in I2, and I'm storing the voltage in V2. Let's call that out.voltage. Right. So what I want to do now is I want to compare the voltages from the first run and the second run, right? So what I'm going to do is I'm going to plot V1, and then I want to hold it so that I use the very same figure to plot V2. So to do that, you use a hold on statement. Just wait for this thing to actually release the plot. I do have a bunch of windows open, so it will take quite a bit of time to execute these commands, which would be otherwise executed in no time if it was just one window open. Goodness. Right. While it's still trying to plot that, I am going to do the hold on statement. It's going to execute that when it's done. And what I want to do after that is plot 2. Then I want to hold off. Just wait for it to execute. Right, so we've got the 2 results here from the T simulation runs. The orange is from the second run. You can add a legend if you want to. I'm not going to do that. And let's add a grid there so that we can visualize this a little bit better. To add a grid, you just type grid on the command window here. Right, and where is our plot? That's better. So what we notice firstly with the initial run, that is the blue curve, we don't even reach the 5 volts that we initially designed it for. We're only getting to about 4.3 volts. With the lighter load, the 20 ohm load, which is the orange plot, our voltage is a bit higher. It's about 4.6, but still, we're not reaching what we designed it to reach. And the reason for that is, remember, we used real components. This inductor has series resistance. There's VDS on over here, which is your on-state resistance. This has series resistance, your ESR, and a bunch of other parasitics that actually cause the voltage to drop. So in essence, we would have to adjust this duty cycle slightly upwards in order for us to get that 5 volts, right? But if we change the load, what we also see is that the voltage, the output voltage also changes, and that's undesirable. Because if you operate this to work at 5, if you design this to operate at 5 volts, then it should operate at 5 volts regardless of the load within practical limitations, of course. It's like saying you're plugging a kettle in your socket plug, and when you plug a kettle, instead of getting 230 volts AC, you're now getting 200 volts, but when you plug in your television, it's 240. Something like that is surely undesirable, and it's obviously a bad design. So in the next lecture, I'm going to take you through how to circumvent that and actually make sure that your voltage remains constant. And one other thing that is actually catastrophic is the overshoot here. For the heavy load, the overshoot is not as significant, but it is still high. We shoot all the way up to 5.9 volts, and we end up settling at 4.3. So that's a large overshoot. And with this one, we shoot all the way to 6.7, and we end up settling at 4.6. That's almost 160% overshoot, and that could be catastrophic to sensitive load. If you're going to have motorized loads or something like that, then they're not going to run as efficiently during this transient phase, because your motor speed, in most cases, will rely on your supply voltage. Right. So I'm going to do the same with the current. It's basically going to tell us the same story, but what I'm interested in the current is the ripple. So let's plot. I'm just going to plot actually just I1 in order for me to observe the ripple at the designed. In order to plot in a different figure, you can pass figure. That's going to generate a new window that has a figure. Then you can proceed to plot what you want to plot. And I named it I1, if I'm not mistaken. There we go. Right, then figure 2 should have current information in there. So we are at, we also overshoot over there, then we undershoot, overshoot, undershoot. There is a bit of ringing, and this is unacceptable. This is unacceptable for most practical applications. So this is something that we need to get rid of. And I'm going to take you through how to do that in the next lecture. We settling at 1.729, and we had expected that in the for the 2.5 ohm load at 5 volts, we're expecting 2 ohms, but because we're not running at 5 volts, we're running a bit lower. That's why our current is so low. So what does this show us? This shows us that in order for us to maintain the voltage across this load constant, we need to constantly update this duty cycle. But it's impossible to carry a screwdriver all the time and constantly adjust that resistor every time you have a new load connected, depending on that load. Surely somebody who's not familiar with electrical engineering wouldn't be able to do that. So that, my friend, is why you need a controller and feedback loops. In the next lecture, that's exactly what we're going to discuss, how to design a controller for this system and sort of keep this voltage level fairly constant and the current as well. And the other thing that we want to do is get rid of that overshoot and that ringing and all of that nonsense. So I'm gonna holler at you in the next lecture. Do like and subscribe. If we've got questions, post in the comment section below, and I'm gonna drop my Telegram handle as well. So if you want to speak to me on Telegram, feel free to reach out, and we'll talk later. Goodbye for now.